So today we're going to be talking about serial communications, and in this presentation we're going to talk about three topics. The first is an introduction into serial communications, what they are and how they work. The second is around the electrical standards, which are things such as RS-232, RS-422, and so on. And then we're going to take a more close look at synchronous and asynchronous serial communications. So let's start with looking at what is actually serial communications. And there are any number of serial communications, but basically what it means is data is being sent sequentially across typically a means of communication. Could be fiber. In this case, we're going to be talking almost exclusively about serial communications over copper lines. You can see here it's just a series of ones and zeros. Typically the data is being sent in binary. That's what we're going to consider today, where a 1 is sent simply by setting the line to a particular voltage or a voltage range, and a 0 is set to a different voltage range. With those, larger voltage swings are preferred. That typically gives you a greater protection against noise. It also gives you greater range. And data can be sent in a number of ways. There's no real limitation. Sometimes it can be sent as a very long string of ones and zeros. Typically it's sent in groups, bytes, sometimes 7, sometimes 8 bits at a time. However, there are other formats such as Baudot, which uses 5 bits. So as you'll see, there's a great deal of variety in it, but it all comes down to a very simple thing, that it is serial communication is about sending sequential bits of information, ones and zeros, down a single line. Let's look at electrical standards. And in the serial, I think most people who have dealt with serial will have come across some or all of these terms. RS-232 probably being the most common and the original of these standards, RS-422 and RS-485. It's very important to note that these are electrical standards. So when somebody is explaining that they are using RS-232, it is quite possible to be compatible with RS-232 in the fact that two devices have the same voltages. In other words, they use the same voltage for a 1 and the same voltage for a 0. However, how the data is actually being sent, in what format, how many bits, and so on, is not defined by these standards. So you are free to use that. Now, there are some fairly common ways that this is done, but they're not part of these standards. These standards are electrical. So let's look at the first one, probably the granddaddy of all. I'd say the original serial communications, not necessarily. There were serial communications. A good example would be a telegraph from the Wild West days, was a form of serial communication, and so on. But when we typically today talk about serial communications, we're often talking about ones and zeros being sent over copper lines, and for that, by far the original and most common standard was RS-232. That defined in 1960. The original standard required a 25-pin connector. It was pretty common after that to drop that down to a 9-pin connector, because so many of the signals that were actually defined are simply not used. Voltages for this are set to plus or minus 15 volts DC. So a 1 was between 3 and 15 volts DC, and a 0 minus 3 to minus 15 volts DC. So that really was the standard. Very common for devices to do plus or minus 5 volts DC. That's on the transmit side. So obviously, when you transmit it over the wire, it is possible to receive lower voltages at the other end, and that's what the range for so plus 3 volts and minus 3 volts is. But it is also common to see people using a plus 5 volt DC for a 1 and 0 volt DC for a 0. That is still very common. And it's non-standard enough or standard enough that you can do simple communications with simply 2 wires. You do need a ground for RS-232. If you just want to transmit data, you can simply transmit data over the second wire. You can do bidirectional, in other words, sending data both directions with simply 3 wires, a receive, a transmit line, and a ground. And if you want to use flow control, 5 lines is very common. And I'll explain about flow control shortly. So as you can see, although this is the RS-232 standard, it's actually not a standard whereby everything is defined and you can guarantee that something that says it's using RS-232 will communicate with another RS-232 device. You will need some further information, and we'll talk about that later. RS-232 typically is limited to pretty short distances because of the use of the common ground and the voltages. It's typically, the standard says, recommends up to about no more than 15 feet. You can run it a little more, but it does suffer from errors for that. For flow control, so original devices were lacking in processing power. So it was quite common that you would start sending data from one device to the other, and the receiving device couldn't keep up with the amount of data coming in. So flow control was put in. This is shown as here. So let's say the DTE device is transmitting to the DCE device over the TX data line. It will assert or set to 1 the request to send line, or the RTS line. The DCE will receive that, and if it's prepared to accept data, then it will assert the CTS line, or the clear to send. In other words, the handshaking is RTS says, may I send the data? And the receiving device says, yes, you may send the data. Now, interestingly enough, this is a typical flow control, but it is only in one direction. So the DTE to the DCE, that data, there is no flow control from DCE back to DTE. It wasn't actually seen as necessary. This was actually put in place for original Bell 202 modems, which actually turned off their transmitter when they weren't sending data. And this is where this flow control comes from. It's very common not to use flow control. It is equally common, particularly now we have so much processing power and things don't, have to stop because of the data coming in. It's very common to just tie RTS and CTS to a high voltage to indicate that you may transmit at any given time and the receiving unit will receive it. But this is the essence of flow control. Would make up about 99% of all flow control. Moving on then to RS-422, it is essentially the same as RS-232, but instead of using a single line for each signal, it uses 2 lines and it uses differential signaling. This means that you can use twisted pair for both the transmit, the receive, and any other lines as well, which is a major benefit. And because of that differential signaling, the range is far greater. And instead of 15 feet, probably closer to 1,200 meters, or about 0.8 of a mile. RS-422 as well, the standard defines that you can transmit from 1 unit to send data to up to 10 receivers on the same line. That is part of the standard. However, not all of those can respond. It is only capable of receiving data back from a single unit. Now, this will be used in the case where perhaps you have a single central device sending out information to perhaps, say, a series of signs where you want to put data on those signs. You could use RS-422 to send the data simultaneously to each of those signs. So that's RS-422, not probably seen as commonly as RS-232, but still a very common standard. The third most common standard is RS-485. RS-485 is somewhat different. It's somewhat similar to RS-422 in the fact that it uses, but it is designed so that the devices can all sit on a bus. And this is typically used for polling devices. And this is how it works. We have a single data line in this case. And in this case, we're showing a series of devices. One of them will choose to transmit. It will talk to all of the others simultaneously. Now, again, this is an electrical standard, so we have not defined how the units talk to each other. What is very common is that each of the devices is given an ID. In this case, I'll choose this as the second one from the left, so we'll call this device 2, transmits data. It transmits to all the other devices on the bus, saying, here is some data, and it will tag it. And it will say, in this case, I am going to talk to device number 1. I'm sending some data to, maybe a polling command. It may say, please, device number 1, please return the data that I've asked for. Once that data has been sent, it will go back to listening mode. All devices will be back in listening mode. And then, because Unit 1 was polled, Unit 1 goes, I have been asked to poll. It sees that there is no data on the bus. It then knows it can send the data back across the bus. So that's very, very simple, very similar for how devices are used a lot for things such as SCADA, polling devices, and so on. Now, there is actually nothing to stop you driving up to as many as 32 nodes, and they can all send and receive data. But as you can see, in this case, they're using a single bus, so they have to, it's half duplex. So one of them will seize control of the bus, will send the data, the others will listen. Once the bus has been given back to its quiescent state, then the other devices may send data themselves. Now, it is possible to do full duplex. It's not quite as common, but it is possible to do full duplex. Works exactly the same way, except now we use a separate transmit and receive bus. So in this case, the central unit can actually transmit. It can transmit to all of them, and at the same time, the receiving unit or the polled unit can actually send data back, and that can be full duplex at the time. So perfectly reasonable to have full duplex with it. You can do that if you want, but it is pretty common to actually not do the full duplex. This is often used for low-speed data. Okay, so that was the electrical standards. So now we're going to discuss the difference between synchronous and asynchronous serial communications. So in basic terms, asynchronous uses lower speeds and synchronous allows higher speeds of data communication. And once we've gone through this, we'll explain how it works. We'll start with asynchronous, and we'll also explain why synchronous communication allows you to generate greater throughput. So asynchronous data looks like this. Now, the problem with that asynchronous communication has is that you have to set both devices up so that the device transmitting knows what to send and in what format, and the device receiving needs to know what to look for and in what format. Also, you have the issue of you don't know when the transmitting device is about to start transmitting data. So it is hard to work out how to sample the incoming data to make sure that you are sampling at the right time to determine whether it is actually a 1 or a 0 that's being sent. So to get around this, what we do with asynchronous is we define on the transmit data line an idle tone. This is where the line is just continuously held as a 1. When you want to start sending data, and in this case I'm showing 8 bits of data, 0 through 7, you would typically transmit 2 start bits, which are zeros. So you can see that on this, as it comes in, it sends 2 start bits. That means that the receiving device can look for an idle tone. Typically, the idle tone is at least 3-bit lengths long. So it can look for a high of 3-bit lengths. It can then receive, as soon as it sees the 2 start bits, it now knows that the remaining part of it, there is now a set number, in this case 8 bits, coming through of data. And it can sample at the rate that it's expecting to see, and it will then sample that and say, yes, the first one's a 1, then there's a 0, then there's a 0, and so on. At the end of that byte, there will be 1 or 2 stop bits, which are high bits, before it goes back into idle. And then to send the next byte of data, it will go through the same process again, sending the start bits, the data bits, and so on. Now, the benefit of doing this means that the 2 devices, the one transmitting and the one receiving, do not need to be perfectly synchronized as to the receiving baud or bit rate. They just need to be fairly close. They can handle perhaps plus or minus 2 to 5% in difference, because every time you send a byte, you resynchronize or reestablish where the start of the data is by the use of the idle tone followed by the start bit. So that's basically how the data is sent over using asynchronous. Now, this is cool, but there is no defined standard for this. It is common that the data is sent as either 7 or 8 bits. Why would you only send 7 bits when you could send 8 bits? Well, the reason is that if you're sending numbers and letters, if you're sending, for example, actually written text, and you want things like punctuation and so on, you don't need 256 combinations. There are 26 letters, there are 10 numbers, there are punctuation marks, special symbols, even if you use capital letters and so on. Pretty easy to send that data over in 128 combinations, which makes up 7 bits. There is also often a parity bit used, just to complicate that. Sometimes the parity bit is put in for error detection, in that if there is a string of data, and you can see the data we're sending here, 8 bits, 3 of them are 1s, that's an odd number of data bits. So you would say there's 3 data bits that are ones. That's an odd number. I am going to set the parity to a 1 to say that there's an odd number of ones. If I then receive 8 bits of data and it has an even number of ones, in other words, a 0 that should be a 0 was actually received as a 1 or vice versa, then I can see that there is an error. I can't correct it because I don't know where that's happened, but I can actually correct it. But we can see that in this case, we have a variety of formats. So the top one has 2 start bits, 8 data bits, 2 stop bits. The next one has 2 start bits, 7 data bits, 1 parity bit, and 2 stop bits. The next one has 2 start bits, 8 data bits, 1 parity, and 2 stop bits. It's reasonable to use just 1 stop bit. It's sometimes there's no parity sent, and so on. So it's really important that the sending device and the receiving device know what they're looking for. They've got to be set up to do the same. So that's all well and good. And we mentioned the fact that we have this idle tone or this idle time at the beginning, and you can send the data and everything looks fine. But what happens if, for example, the transmitting one sends at a slightly slower rate than is expected? Now, this example is going to be a little extreme just to demonstrate the point. But we can see here, up here, that this was meant to be sending at a known rate. And I'm going to say that this is a little bit slower than was expected. So when the data that was sent here is 10010010, and then when it's received, when you're looking for receiving, the receiving device thinks that the data should have been sent faster than it actually was. And you can see here that it's thinking that it would have received the data by the end of, not even the end of the first stop bit. So when it does its sampling in the middle here, it will take the first one, it will look, and you can see by the long green arrow that it actually looks at that as a 1. That's cool. That's what it was expecting. The next one's a 0. That's good. The next one's a 0. That's good. Ooh, and then you can see that the next one is right on the cusp between a 0 and a 1. I'll give that a 0, and then a 1, and then a 0, and a 0, and a 1. So you can see because the data was sent too slowly and was then sampled at the correct rate, or the vice versa, but the data was sent at the right rate and was sampled too quickly, you can see that there's a slippage between these two, and that means that there are errors on the data. And this, although this is an extreme example, this is probably showing around 10% slippage. What we can say is, if it was 1% and you sent a string of 50 bytes, all in a row without the idle tone, without the start and the stop bits, it's almost certain that you would see this effect over that amount of time. So it's really important that you do send that. Now, I mentioned before that asynchronous, not as fast as synchronous. There's a simple reason why. One of them is this potential slippage, but the other is the fact that if we take this data at the top here and we say that the idle has to be 3-bit lengths, the start bits have to be 2-bit lengths, and the stop have to be 2-bit lengths as well, then we can say 3 for the idle plus 2 plus 2, that's 7 bits just to handle of essentially overhead, and then you send 8 bits of data. So what you can see is, in that case, that effectively you are halving your data rate because you are using essentially overhead in the terms of idle, start bits, and stop bits. So that makes it that, and the fact that both the transmitting and the receiving device are not totally synchronized means that it is typically limited to slower data rates. So that's asynchronous. Let's talk about synchronous. So synchronous uses an extra wire or signal called the clock, and the clock is as I said, an additional line that is used. And what the clock does is it tells the devices where you could sample the data. So in this case, we are going to do it on the falling edge of the clock. And let's say that I transmit some data from a device, and at the same time I send the clock. What I do is I make sure that the falling edge of the clock, that's shown in the red circle, is right in the middle of where the bit is defined. So if you look above that, you will see it's right in the middle of the 0. And then the next one along is right in the middle of the 1, and so on. What this means is that it's very easy to determine what data, where you should be sampling the data, because the clock tells you where to do that. And this means that if for example, we slowed the data down, and at the same time we slow the clock down, there's no errors being generated, because the receiving device can look at the clock and go, I know where to sample the data to make sure I get the right bit. Similarly, if I speed the data up and the clock at the same time, I still get the same data reading. Now, the benefit of this means that because of this, I can send long strings of data without the need to keep sending the start bits and the idle tones and all the rest of it. So this means that the overhead is greatly reduced. So do I need start and stop bits? Absolutely not. I don't need the idle between the bits. I don't need the start bits. I don't need the stop bits. I don't need to go back to idle at the end of it. So inherently, you can see by just taking that overhead off, it's a great deal more efficient. Now, you may have noticed that there is one issue in this, that if you do this and you're just sending a big continuous data stream, the question is, where does the start of the byte happen? And how that is typically handled is typically within the data stream, there is a particular pattern that is used that designates the start of data. So, for example, if you turned on a transmitter and started it transmitting, and then a little bit later you turned on the receiver, and the receiver starts receiving it, it's got no idea where you are at in the transmission. It's just receiving ones and zeros. So it will then sit looking for a particular pattern of ones and zeros, and when it sees that, it says, that is the start of this data transmission. Typically it's 3 or 4 bytes worth. That says, right, after that, that's the start of the data. I know where the data is, and it goes forward. So the amount of overhead is significantly reduced. This is a continuous data stream. It's got far higher throughput because you can significantly increase the data rates because you have the clock. However, you can still use flow control. If you want to use flow control for clear to send and request ready to send, you may do that. But typically for synchronous serial, you don't actually need to use the flow control, but you can if you want to. Now, important thing, how many clocks are there? There is only one. There is only one clock, and we'll show here how it works. So we have the clock comes from one device to the other device, and data that is transmitted will be transmitted synchronously with that clock. Okay, so we look at the device that is transmitting the clock and the data, and make sure that the data is sent at the right time. On the way back, the device from the right sending data back to the device on the left, that also is synchronized with the clock. In other words, it knows that it should start sending, it should make sure that when the clock goes from positive to negative, it is in the middle of sending its particular data. So it can use the incoming clock to synchronize its data on the way out. When it's received by the other device, obviously that data is received, and that data is actually decoded by using the outgoing clock to synchronize the incoming data. Now, of course, we do have the TC Communications, so we do make products that sit in between two serial devices. So we actually have two serial devices, and we might want to transport this, say, using our JumboSwitch product over IP. So that's what the blue box designates in there. But we're talking about the serial stuff. So let's say that the device on the left is transmitting across to the device on the right. So we see a clock going across. Okay. So the clock is sent from the device on the left to the TC products, which receives it. The TC product regenerates the clock or passes the clock through and sends it to the device on the right. We can send the data, obviously synchronized with the clock, and the data that is synchronized with the clock comes out of the TC product, which is cool. And data going back, data going back, this data goes back and it is synchronized with the incoming clock, and the data going back is synchronized again with the clock on the left. But this is pretty interesting because remember that the data needs to be synchronized with the clock on the left. The data going to the TC products and coming from is synchronized with the clock on the left. Similarly, the data coming out of the TC products and going back into the TC products on the right is synchronized with the clock on the right. Although the clock may well be passed through, it is possible that the clocks will be out of synchronization with each other, but they will be in synchronous with the data itself, which means that the data that's being received will be received correctly every time. Now, there is a different approach, which is it is possible that the TC product, for example, a JumboSwitch product, can be set to actually generate the clock itself. And this is an interesting one because we send the clock from the TC products out to the device. We send another clock out to the device on the right. We send the data through. The data goes through on that side. And again, the data is synchronized with that clock on both sides, but the clocks aren't necessarily synchronized together. And the data comes back the other way. Again, on the right is synchronized with the clock on the right, and the data on the left synchronized with the clock on the left. So this provides synchronization, and this means that none of the original devices are generating the clock. And this is perfectly acceptable way of doing it. And although we showed originally the clock being generated from the device on the left to the one on the right, of course you could set it up to go the other way. Or you can set it up to have the clock in the center, generated by the TC product. The important thing to remember in all of this is when each device will either send or receive the clock, and it will use that to either send or receive the data to make sure that the data is synchronized to the clock. And that's the most important part. So that really covers synchronous communications. Hope you found that useful.